looks like that. That would be a constant force, and so the work is just the area underneath. So it's whatever that force was times the displacement. That's just straight up multiplication. If force is not constant, it's still the area underneath. It's just not, for a triangle, we got that. If it's a curve, then we'd have to get into, doing some antiderivatives. We don't need to go that far. But I want to point out that the work, if the force is directly proportional to displacement, it's still the area underneath. So this is some force right here, and that is some displacement. So what's the area of a triangle?
1/2 times base times height.
My base is the displacement, and my height is the force. I guess we're dealing with magnitudes here. So if this is a spring, in other words, if the base Hooke's law, they're directly proportional, so it should be linear there. The force is equal to, well, K delta X, so I'm left with 1/2 times the displacement. My notation's getting sloppy here. Times the magnitude of the displacement times K delta X. In essence, what we're left with is 1/2 times the spring constant times the displacement squared.
So
It's questionable. Do I really want to get into why I can justify getting rid of the vector symbol? I think I'm just going to go with trust me. If you want to know why I justified getting rid of that, I'd be glad to answer it, but otherwise, just trust me. This is the magnitude of the displacement. So that would be the work. If I take a spring and I stretch it out, that is the work that I am doing in order to stretch it out. But we still need to connect it to kinetic and potential energy. So let's do that. Did you talk about conservative and non-conservative forces?
that's not kind of ringing a bell.
No, I don't believe
Yeah,
so.
that's not ringing a bell for me.
Okay.
Yeah, that's not familiar to me either.
All right, so forces are either conservative or non-conservative. Within the context of energy, what do you think a conservative force does concerning energy?
It just converts the energy into something else.
What do you mean something else?
Like friction like with friction, energy is converted into heat.
Yeah.
And force that is going against the movement of the object.
Yeah, friction is an example of non-conservative.
Oh. And I don't know.
Anyone else want to take a shot at what conservative forces do?
It keeps all the energy within the system.
Yeah. It conserves energy.
The final energy is equal to the initial energy.
Right. If the conservative forces are the only forces doing work, that's exactly it. So we have work here is force times displacement. We also have, we can break, basically look at it from the point of view of total work, conservative work, and non-conservative work. And that W looks like two V's there. Let's see if we can do that a little bit better. The total work, well, we can actually go through that. Total work would be the total force times displacement. We'll come back to those in just a second. And what's the total force equal to? Newton's second law.
Mass times acceleration.
So this is the mass times the acceleration times the displacement. And what is acceleration times displacement?
That's,
Probably be chapter 2 of the textbook. Because it's usually chapter 2. Not chapter 2 of your textbook. Where do you do that? It's like chapter 6 of your textbook. Yeah, chapter 6 of your textbook. Remember the relationships between position, displacement, velocity, and acceleration? The math equations?
Oh, the derivatives? Like are you talking about the relationship between them, or?
Yeah, not the constant acceleration ones. Like VF equals VO plus AT. Not ringing a bell?
Oh,
yeah, that's right.
Yeah.
I was just trying to.
There's usually a set of 4 equations. Some textbooks will do 5. So let's bring that up, we'll pull that up over here. So the final velocity is equal to the initial velocity plus acceleration times time.
yeah.
Sometimes this is written as VO instead of VI, and sometimes it's written as VF instead of V. For what I need, I wanted to put down VF. You happen to remember any of the others or part of another one?
That's a while ago.
I need a refresher on this.
Yeah,
I'm getting the impression that you have not studied this every day since that course.
that's correct.
Yes.
Okay, as long as I understand. There's also delta X or delta S or whatever
Yeah.
letter you're using,
So the VT plus,
VIT,
or yeah, VFT plus AT squared,
plus 1/2 AT squared.
1/2 AT squared.
And then isn't there one that's VF? It's VFT, or no, I mean, isn't it delta X, VFT plus 1/2 AT squared, or am I thinking? I thought-
Oh, there's also a,
Minus.
there is a VFT minus 1/2 AT squared.
Yeah.
That's the one that some textbooks don't bother writing down, but some do. I'm guessing yours did it.
Yep.
There's 2 more then. There's another delta X one, and then there's a VF squared one.
I remember there just being 4.
No, there was 5.
There was
Miss
5.
Sassen, she wrote the other one, the BFT. Yeah, she wrote both of those.
That one, okay. I
Um,
tend not to, so that's, but all depends on, no problem.
Isn't VF minus VI?
Call it VF plus VI. Basically, it's average velocity times time. So if acceleration is constant, then the average velocity is just the average of the first and the last one. And then the last one here. Just, anyone have, ringing any bells here?
I know it's VI squared something, but I don't remember the other part of it.
The one that actually matters for what we're doing here.
218?
No, this is the one without time.
Two.
Each one of the equations, given displacement, initial velocity, final velocity, acceleration, and time, there's 5 quantities there. If you're missing a quantity, each of these equations is missing a quantity. This is missing displacement, this is missing VF, this misses VI, this misses acceleration, and this doesn't have time. These are what I refer to as CAKE, constant acceleration kinematic equations. So just for future reference or in a video, if I make a reference to CAKE formulas, this is what I'm talking about. So from that last equation right there, if we solve for acceleration times displacement, this becomes mass times VF squared minus VI squared divided by 2. And I'm just going to rearrange that. That's 1/2. Actually, I'm going to distribute the 2 in the mass there, so I get 1/2 mass VF squared minus 1/2 mass VI squared. You see that final step?
I don't remember this.
What is 1/2 mass times, this is speed squared at this point, 1/2 mass times speed squared?
Delta KE. Oh.
You jumped a step, but
Oh.
the 1/2 mass times speed squared is just K.
Yeah.
So this is K final minus K initial, which is,
Oh,
Yeah.
yeah.
Delta K.
There you go, yeah.
so the total work on done on an object is equal to the change in kinetic energy of the object. All right, so here's a little bit. When I was doing IT consulting, we were up in what they refer to as boot camp, and we were doing a bunch of programming, and at some point somebody comes into the room and says, all right, everybody up. We're gonna do jumping jacks. And I being one of several people, look at them strangely going, what? And she goes, this is serious, get up now. We're doing jumping jacks. Because they didn't want people to be stuck at a desk doing this all day. They wanted people to get and actually move around. So, I am serious about this next bit. When I ask you, what is the formula for kinetic energy? I want all of you in unison to say 1/2 mv squared. 30 years from now, when I run into you and you go, wait a second, hey, Dr. Fox, and I go, hey, Aaron, because I'll remember, of course. Usually after you leave, I'll remember, but we exchange pleasantries, and then I should be able to go, what's the formula for kinetic energy? You should immediately know 30 years from now.
1/2 mv squared.
That's right. See, it's already gotten practice. All right, so in unison, all 4 of you. What's the formula for kinetic energy?
1/2 mv squared.
That wasn't exactly unison, but.
That wasn't. That was doing the rounds. Let's try it one more time. I want to hear a chorus of angels. Here we go. What's the formula for kinetic energy?
1/2
mv squared.
1/2 mv squared.
You seem to keep repeating yourself.
I struggle with timing.
Okay.
So-
3.
All right, well, that was closer. So at various points during the course, I might, again, ask you what's the formula of kinetic energy, and then all of you will, of course, at some point, in unison. It'll be beautiful. Tears of joy will stream down my face. It'll be a lovely sight, and it'll be videotaped. Everyone will know. All right, so. But if I ask you what's the formula for potential energy, the proper response is, which one? There is one formula for kinetic energy, although it does get disguised with the rotational motion, but there are many formulas for potential energy.
Because it depends on the type of energy.
It depends on the type of conservative force.
Oh.
Every conservative force has a potential energy formula.
Like, what would, for heat? Just as an example.
With the,
I'm just asking what kind, like you said, there's many conservative forces depending on the type of energy, and I figured heat would be an example of it.
heat is exchange of energy because of difference in temperature. Temperature is directly related to kinetic energy.
Oh.
So if I have an object falling, so I just take this marker and I just let go, what is the conservative force acting on it as it falls?
Acceleration.
Sorry, what did you say?
Acceleration due to gravity.
Looking for a force?
Force of gravity.
Yeah, force of gravity. Or weight in this particular case. That is a conservative force, so there's a potential energy associated with it. What is the formula for the potential energy associated with weight?
Probably
Mass times gravity.
Yeah, that sounds about right.
You're missing something.
Oh,
Two things if I'm nitpicking.
is there a height in there somewhere?
There's a height in there somewhere, that's one of the things. And the other one is, you said mass times gravity. It's more properly,
Mass times the acceleration due to gravity.
thank you.
Oh.
Times height.
Yes, MGH.
Oh, okay.
Yeah, that's the classic one. Most people think that's the formula for potential energy. No, that is a formula for potential energy. All right, so if there is a non-conservative work is equal to the non-conservative force times displacement, and that should be non-conservative force times displacement. It's called non-conservative because energy is not conserved, which means if there's non-conservative work being done, it's causing a change in energy, and so that is equal to the change in energy. Not really deriving that one, just sort of spewing that.
And of course, one of those non-conservative forces could be friction.
Yes. Friction's the classic non-conservative. So if we think about work total is equal to the change in kinetic energy, which is what we just sort of derived right there. We could have done it with calculus and end up in the exact same spot. Total work is equal to, well, I got two types. I've got conservative work plus non-conservative work is equal to the change in kinetic energy. Non-conservative work is equal to the change in energy, so this is work conservative plus the change in energy is equal to the change in kinetic. So this is work conservative plus, well, change in energy is the change in kinetic plus the change in potential energy. So that is my change in energy. Got my two types there. Delta K cancels out, bringing delta U over, and we end up with the work, conservative work is equal to the negative change in potential energy. This is what connects the conservative force to potential energy right here. So,
That makes sense, because if you drop the marker, it has potential energy, it loses it, and there's conservative work done. That makes sense.
or attached to a spring, pull a spring out, you let go, it has potential energy in the spring, and then the spring converts it into kinetic energy as it goes. So the perfect ideal elastic force from a spring, or an ideal elastic material, that's a conservative force. Gravitational forces are conservative, whether it's weight or you're talking about outer space. Electric forces are conservative, magnetic forces are conservative, and well, strong forces and weak forces, but that's well beyond the scope of the course.
That strong and weak, is that quantum or nuclear physics?
Yes.
Didn't we list these in?
Nuclear?
No,
I
actually,
don't think so.
yeah, no, that's nuclear. It's at the nucleus. And it's described using quantum physics.
Oh, okay. I was just curious.
It's not like I can't write up, oh, here's the formula for potential energy for those.
Oh.
It's far more complex than
right.
that.
Yeah, yeah, I'm already I'm kind of just like watching some of this and then just writing down some of it because I'm getting lost.
All right, well, we're about to connect it back up to what we had been doing.
Normal force.
Non-conservative.
I feel like we listed these in the Satson's class.
Yeah, the list of the four forces I just gave, magnetic, electric, elastic, and gravitational, those are basically the conservative forces that you'll deal with unless you get into really advanced physics. Pretty much any of the others, non-conservative. Friction, normal, tension, buoyant, because that's in essence a normal force at its heart. All right, so as I take my spring and I stretch it out, I'm doing non-conservative work. The spring is doing conservative work because the spring is exerting a force on this as it's being stretched out. The way I described it, this is basically the work I'm doing here. The spring is doing the exact same amount of work because as I take it from here and I pull it out to here, there's no change in kinetic energy. I'm just pulling it at a constant speed. So since my change in kinetic energy is 0, that means the total work is 0, which means that the work being done by the spring, the conservative work being done by the spring, has to match the non-conservative work being done by me. So as I stretch it out, the conservative work is negative because I'm pulling it this way, but the spring is pulling it that way in opposite directions. And so it'll be a negative on this side, negative on that side, the negatives cancel out. So my change in potential energy will be equal to 1/2 K delta X squared. Generally, you would write that as the spring potential energy or elastic. I tend to use S for this, even though it's really an elastic force, an elastic potential energy from an elastic source, because I reserve E for electric. So we have a potential energy formula dealing with the spring. Questions to hear before we do the next thing?
What is the next thing?
Well, it's actually, I think, 5-minute break might be in order. Why don't you take 5, stretch your legs? Just bring that energy level down just for a little bit. I am gonna just keep it running because I don't wanna get into the next bit and then suddenly realize I forgot to record. So if you need to talk about something that you don't want recorded, we can step to the other room, or if it's not with me, you can step outside.
Alex told me he talked to you this morning.
He sent me an email.
Yeah.
Yeah.
He said he had a migraine, so he wasn't gonna make it today.
Yeah.
And then I let him know that the quiz in the lab are moved to Monday.
All right, thank you very much.
I had a question for you, not related to this stuff though.
Okay.
What would you say? You did a quantum. I'm trying to think. What's the most advanced physics you did?
That I did?
Yeah.
Probably the course that really was beyond my ability was when I took a general relativity course.
Oh. Yeah.
So,
there's
but you get, I mean, physics progresses up to a certain point and then it sort of branches out. And so, I mean, a person whose mind thinks the way general relativity does might find difficulty in another discipline. My doctoral dissertation was in high energy physics. And so I spent more time on that.
Right. Sometimes I wonder how this course would relate to me being a technician or working with robots, because what I've mostly been doing was working with things that have a voltage of at max 120 volts. But not saying that out of criticism or saying that I don't like the course. I'm generally interested, even if the math might be a bit much.
Yeah, how much any course will affect your future career, I don't know. I assume, I mean, we're dealing with basically elastic materials right here and dealing with waves. You will eventually get into the light aspect of it, as in sunlight or other forms of electromagnetic radiation,
Yeah, like
which could
lasers.
affect as you're sending the signals to the robot or the robot sending the signals back, that's usually in the form of electromagnetic radiation.
Yeah.
So potentially, more direct connection in the second half of the course.
Also, how does Hooke's law correlate to light and possibly sound? Is it the resonance? Because I tried looking for YouTube videos explaining the correlation with sound and Hooke's law, but I noticed oscillations, and that's where I kind of sort of thought there was a connection. I don't know if that's true or not.
If I take a charged particle and I oscillate it back and forth in harmonic motion, simple harmonic motion, it's going to create an electromagnetic wave. Actually, it'll create an electromagnetic wave which we can describe mathematically. If it's behaving more erratically than that, then it'll be a more complex version of what we've done here.
Oh, okay.
So, sorry, Aaron?
Oh, no, I'm sorry, and we're gonna be learning about Doppler effect,
Yeah.
correct?
Yeah.
That's on my radar. was based off of.
Okay,
But it didn't spin. It was basically like it had 4 faces, one on each side of the ship, and it had phase shifters that would point the beam of
Oh.
RF in different places.
okay, so
The-
more directed.
Yeah. Yeah, well, like say like it would search, so it would just search a wide area and it'd pick something up, and I guess some sort of algorithm in the computer would like, okay, it's moving at this angle, speed, and height, it's gonna be over here next, so it shoots a beam ahead of time
Okay.
to catch it, processes it, and then like say if it goes back this way, it's like, oh, it's not there no more, let's search the immediate area around where it was, and then pick back up on it.
Okay.
Oh, interesting.
It's all done by a computer.
Yeah, no, I'm just, it's all part of that amazement of what they can do,
Yeah.
Especially
When
in
the-
the military.
Yeah, I mean, all physics leads to weapons, ultimately.
And also it could communicate with missiles too. That's pretty cool.
I was thinking of during the first Gulf War when they talked about, they had bombs that, we want to put that bomb through that window.
Yeah, they'll do it.
They
Yeah.
can do that now.
Yeah, laser guided. Yeah, it sounds like laser guided.
Even on land they have that. It's tow missiles. It's basically just one long cable.
Yeah,
Cable. It's basically a missile with a cable on the end of it. You point with the laser and it follows it.
And
It's crazy.
still, I'm still amazed by Palm, so, Palm too.
No, Palm, yeah.
yeah. Oh, yeah. I remember hearing they made something similar to that with an oscilloscope or some kind of device like an oscilloscope.
Yeah, the first version of Palm was done.
It only works for like 2 miles.
Can't remember, it might have been.
It's like last defense.
Yeah, I don't remember. I saw it on a Wikipedia article.
Like a missile's coming in all of a sudden.
Yeah.
But yeah, thanks for sharing that stuff.
You gotta think it's that close, you hit it, it explodes, you're still gonna hit it.
My 2 cents.
Yeah,
Yeah, it's like a missile coming in.
math might be much, but I do have some. I am genuinely curious.
Back over the horizon, find you.
That goes a long way.
over the horizon So you can't track it. It's RF, the RF can bend over the horizon, but,
Alright, so let's get back to spring on the frictionless ramp here. I think this was 3 meters. And then it gets stretched out to an additional 2 meters. We had a 4 kilogram mass sitting on it. We'd already established that the spring constant was 24.5 meters per, newtons per meter. At what point, as I pull this thing out to the 2 meters, I let go, now oscillates back and forth, at what point is it gonna be at its maximum speed?
on the speed,
When it passes 0 meters, displacement.
Yeah, at this point right here, so let's take a look at that from an energy point of view. Once I let go, the only forces acting on it, the only force doing any work is the elastic force, which is conservative. The force due to gravity acting down is not doing any work because movement is perpendicular to that. And the normal force acting up is a non-conservative force, but it's not doing any work because it's perpendicular to the movement. When I did the multiplication, notice I had a dot in there between the A and the delta X. That dot indicates you're multiplying the parallel parts. It's called a dot product. So energy is conserved. Two types of energy, got kinetic plus potential. Oop, wrong letter. We plug in formulas here. This is 1/2. Oh, man. Doing this kind of thing last night too. 1/2 mv initial squared plus 1/2 k delta x initial squared is equal to basically the same thing but final. 1/2 mv final squared plus 1/2 K delta X final squared. This is just generic. We haven't really established anything of great importance yet. But now let's do it. Let's make the initial position when I first let go. Not when time is equal to 0. We don't care about time. Time's not showing up anywhere over there. I'm just going to establish this point right here. At this point, my speed is 0 meters per second. At this point right here, my speed is maximum. Because once it passes that point, the spring is going to be pushing on it, slowing it down. So this is 0, because my initial speed is 0. This is my initial, my final. That is not 0. Well, we'll come back to it. Here, this is not 0, but this is. Because when I pass equilibrium, my displacement is 0. So that's 0 because delta x is 0. So my equation has reduced down to this. If I multiply by 2, my 1/2s go away. So I'm left with k delta x squared is equal to m v final squared. So my final speed squared is k delta x squared over, that should be initial right there. So k delta x squared over m. And so that's 24.5 newtons per meter times delta x, which is initially 2 meters, divided by the mass, which is 4 kilograms. Oh, that should be 2 squared. And we get 24.5. And so VF is equal to the square root of 24.5. .9. I suppose I can still read it. Nah, it's gotten buried. 4.94.
Yes, or 4.95.
Okay.
Close
Units?
enough. Meters per second.
And that is the magnitude of the amplitude of our velocity equation that we had just had.